Hi, I'm Scott Vaughn. I recently made a video called the VisViva Lab, in which I used the game Kerbal Space Program to illustrate conservation of energy and angular momentum in the orbital trajectories of satellites and spacecraft. Kerbal Space Program is such an amazing tool for inspiring learning in math and physics, and it truly has inspired me to continue that investigation, now with real-life data. In this video, I will download orbital ephemerides from NASA's Horizon Online Orbit Tracking System, provided by the Solar System Dynamics Group at the Jet Propulsion Laboratory at Caltech. Ephemerides are tracking data that include a combination of observed and predicted position and velocity data for celestial objects. I'll use Excel to analyze that data and explore conservation of energy and angular momentum for several real-life objects in our solar system. In the previous video, I analyzed suborbital, circular, elliptical, and hyperbolic flights by collecting data on the changing position, velocity, and pitch of different spacecraft in Kerbal Space Program. In that video, we confirmed that even as the position, velocity, and pitch of orbiting spacecraft changed during flight, the orbital energy and angular momentum remained the same. That is, both energy and angular momentum were conserved. It's important to point out right away that Kerbal Space Program assumes two-body physics in calculating the gravitational forces and the resulting trajectories. That is, orbits and trajectories are determined based on only two masses at a time. That's great because that's exactly the assumption that we make in beginning math and physics courses in school and in the courses that I teach. With two-body physics, orbits are conics and are described with the relatively simple equations of circles, ellipses, parabolas, and hyperbolas. With two-body physics, positions and velocities can be exactly predicted by the equations of the conics, forwards and backwards in time for eternity. Real life, of course, is not so simple. In real life, objects follow trajectories determined by the gravitational influences of multiple other objects, all simultaneously interacting with each other. This is what's referred to as the n-body problem, and it's much more complex than the two-body problem. In fact, in general, there is no formula or equation for plotting exact position and velocity for three or more bodies in orbit all the time, forwards and backwards for eternity, the way that it could be done for two bodies. With three or more bodies, position and velocity are determined by starting with the equations of the conics and then adding perturbations or adjustments based on the sum of the positions and velocities of all the other objects in the system, computing those results forward or backward one step at a time. This is what's already computed and provided in the ephemerides data on the Horizon system from NASA. In this video, we'll use that data to look at the trajectories of several interesting real-life celestial objects, following essentially elliptical or circular or hyperbolic trajectories, but with the orbital perturbations included. And these objects include the near-Earth asteroid Apophis, the Tesla Roadster carrying Starman, the International Space Station, and the interstellar object Oumuamua. We'll compute specific orbital energy and angular momentum for these objects and investigate the extent to which these values remain constant and why they might vary, and confirm our results with other sources such as data on Wikipedia, the NASA EYES website, and in the simulation game Universe Sandbox. Now let's get into the first example with the International Space Station. What you're looking at here are the position and velocity data for the ISS from NASA's Horizon system. The beige columns are the downloaded values, and the blue columns and the bright yellow columns are values that I've calculated here in Excel. The rows of the table represent 10-minute intervals on June 25th from 12 a.m. to 11:50 p.m. on that day, a total of a 24-hour period, about 144 rows in total. In this data, we are looking at position and velocity of the ISS during the entire day, representing roughly 16 complete orbits around the Earth. The first three columns here are the x, y, and z components of a position vector with distances measured in kilometers from the center of the Earth. The next column in blue is the magnitude of the position vector. That's found by computing the square root of the sum of the squares of the x, y, and z components. And this represents the distance from the ISS to the center of the Earth, again measured in kilometers. And after that, the next column is found by taking the distance from the center of the Earth to the ISS and subtracting off 6378 as an estimate for the radius of the Earth in kilometers. And this gives us the estimate for the altitude of the ISS above the surface of the Earth. We see this results in values between about 405 kilometers and 423 kilometers, which is consistent with what we would expect for the orbit of the International Space Station. In the next three columns, we have the velocity vector, specifically the x, y, and z components of the velocity vector in three-dimensional space, here marked out as Vx, Vy, and Vz. After those columns, I've used Excel to compute the magnitude of the velocity vector. This is the speed of the station, and I've converted that into kilometers per hour and miles per hour in the following columns. We see this indicates that the ISS is traveling at about 7.67 kilometers per second, or at about 17,100 miles per hour, values all consistent with what we can find when we look this up on Wikipedia. The Wikipedia page for the ISS provides some quick, easy to reference station statistics here over on the right column. And for example, we can see that the perigee altitude and apogee altitude, lowest and highest altitudes in the range of 413 kilometers to 422 kilometers. We can see orbital speed here at about 7.66 kilometers per second, or about 17,100 miles per hour. And also note that the period is about 93 minutes in total. That is the time it takes to complete an orbit around the Earth, and roughly 15 and a half orbits per day. Next, I use this formula for the specific orbital energy. That is, epsilon is 1/2 v squared minus mu over r. So here, epsilon is the specific orbital energy, v represents the speed, mu is the gravitational parameter, in this case the gravitational parameter for Earth, and r is that radial distance, the distance from the center of the Earth to the orbiting body, in this case the International Space Station. So this is the same formula that I used in the previous video in Kerbal Space Program for specific orbital energy. It's called specific orbital energy because we're dividing out the mass of the orbiting body. In KSP, I took measurements at just 2 points in time during an orbit and looked for conservation of energy and momentum. Now here I have 144 points in time that I'm doing these calculations for. And we see here the value for the specific orbital energy. It's around negative 0.293 to maybe about negative 2.94 times 10 to the 7. That's in kilometers squared per second squared. Or about negative 29.4 megajoules per kilogram. And it remains nearly constant during the roughly 16 orbits represented in this data. Also notice that the value is negative. That's consistent with a bound orbit. We'll see as we proceed with other examples that anything in a bound orbit around another body will have a negative orbital energy with respect to that body. We'll see objects with zero or positive orbital energy are on escape trajectories. And just like in the previous video, I want to calculate specific angular momentum. Now, because I have the position and velocity vectors, I could take the cross product to find the angular momentum. But in the previous video, I used only the magnitude of the angular momentum. That's all I needed then, and that's all I need for my purpose now. This means that I can use the formula shown here. This is the specific angular momentum h, and r represents the magnitude of the position vector, v is the magnitude of the velocity, and theta is the angle between the position and velocity vectors. But obviously, to use this formula, we need to know the angle theta. Now, to find that angle, what I do is a dot product of the position vector r and the velocity vector v, and then I use the arc cosine to find the angle theta that's between those two vectors. This is also interesting in and of itself because I can confirm here that the orbit is nearly circular. because the angle theta is nearly 90 degrees throughout all of the data, and thus the pitch is about 0 degrees throughout all the data as well. The pitch is found by subtracting the angle theta from 90 degrees, and the result is what I would expect in a nearly circular orbit. In a circular orbit, the direction of the velocity is perpendicular to the radial vector. In KSP, we could measure pitch from the navball display, but here, now, with the horizon data, we don't have a navball display, but we can find pitch using the velocity vector. One reason that computing magnitude of specific angular momentum is my goal here is because I can use that along with specific orbital energy epsilon to find the eccentricity of the orbit, just as I did in the video with KSP. And to compute eccentricity, I use this formula. Eccentricity, E, is the square root of 1 plus 2 times epsilon, the specific orbital energy, times h, the angular momentum squared, all divided by the gravitational parameter mu squared. The result of doing this with the collected data for the ISS also confirms that the orbit is circular, or very nearly circular, because the circular orbits have an eccentricity of 0, and that's what I'm getting here. Finally, this reminds me to mention why this video is called the VisViva Lab. It all started for me with learning about orbital mechanics in Kerbal Space Program and discovering something called the VisViva equation, some of the mathematics that is fundamental to understanding orbital mechanics. I learned how the Vis-Viva equation was derived, and in the process, I realized the importance of conservation of energy and angular momentum in understanding and deriving the Vis-Viva equation. In other words, this project became the VisViva Lab because I realized how important these concepts of conservation of energy and angular momentum were to understanding the Vis-Viva equation. What I've observed here with the data for the ISS is that energy and angular momentum are nearly constant, but not exactly constant, and this is as expected. Of course, I knew it wouldn't be exactly constant. I expect all sorts of reasons for minor fluctuations in these values. For example, measurement errors and rounding errors come to mind immediately, but also so does the influence of the moon and the sun in the orbit of the ISS, the fact that we are now considering an n-body problem. And there are other forces like small amounts of the Earth's atmosphere that extend the altitude of the ISS and thus produce drag on the station. And there are other factors. For example, Earth is not perfectly spherical or uniformly dense, and this affects the gravity field around it. And also, the ISS does its own periodic orbital maneuvers, which introduce an external force on that orbit. And then there's the pressure from solar radiation on the station. So all these factors lead to fluctuations in the orbital energy and angular momentum of the station. In analyzing these fluctuations, I see that the energy oscillates between about negative 2.93 and negative 2.94 times 10 to the power 7. And I observe the specific angular momentum oscillates between about 5.20 and about 5.21 times 10 to the 10 square meters per second. And I've computed the mean, median, standard deviation, and range in these values, and I observe that the range in values from the largest to smallest values that are recorded is less than 1% of the mean value during the interval in which this data is collected. So pretty nearly constant, a very small variation. Also, as I look at the oscillations in altitude and in the specific energy and angular momentum, I see the period of the oscillations in altitude are about 90 minutes. That's fascinating because the period of the ISS orbit is about 90 minutes. However, the oscillations I see in energy and momentum are about 40 to 50 minutes in both of those cases, and that is about half the period of the ISS. I'm not sure why that is. I'd be interested to read any comments that anyone might want to leave as to theories that might explain that frequency there in the oscillation for energy and momentum. Now, let's do a similar set of calculations for the near-Earth asteroid Apophis. Apophis is fascinating. First discovered in 2004, its name is the Greek name for the ancient enemy of the Egyptian sun god Ra. Apophis was the uncreator, an evil serpent who embodied chaos and was the opponent of light and order. Wow, that adds a little drama to a math video, right? And how about this? Apophis will make a close approach to Earth on April 13th, 2029. Yes, that's Friday the 13th in April 2029. Mildly interesting? How close? What's the risk? Apophis will pass within about 20,000 miles of Earth on Friday, April 13th in 2029, but there's essentially zero chance that it will hit Earth. Why did the probability of an Apophis impact in 2029 go up when it was first discovered before it went down to zero? According to the website from the Planetary Society, soon after its discovery, more observations of Apophis refined the asteroid's trajectory, and the range of trajectories still included Earth. More observations refined its path around the Sun and excluded Earth, bringing the probability of a 2029 impact down to zero. Still, it's a really close flyby. The closest approach distance is only about 5 times the radius of the Earth itself, and puts it about 10 times closer than the Moon to Earth at the time of that nearest approach. And by the way, thank goodness it doesn't hit the Moon either. Will it be visible? Yes, but according to the Planetary Society, it will appear as a bright star only in Europe, Africa, and Western Asia. So how big is it? And how does it compare with the asteroid that killed the dinosaurs? So Apophis is about 450 meters, about 1,500 feet, on its longest axis. And the asteroid that killed the dinosaurs was much bigger, probably 10 to 15 kilometers wide. I've downloaded position and velocity data for Apophis from the Horizon system and run the same calculations as before that I did with the International Space Station. And the rows in this table represent each month on the 13th of the month from June 2023 to October 2031. That's about 100 data points, representing a little over 8 years total. And of course, the most significant observation here in these calculations is that sudden jump in the specific energy and angular momentum immediately following that April 2029 close approach. Also captured in this data is the negative specific energy, representing a bound orbit about the Sun and the eccentricity of about 0.2. Interestingly, while the radial distance between Apophis and the Sun does increase significantly after that 2029 close approach with Earth, the orbit eccentricity does not appear to change that much. Perhaps it decreases slightly, always less than 0.2 here in this data, the way that I'm calculating it, but that could be a topic for a further exploration later. And I've also downloaded ephemeris position velocity data for Apophis for April 13th, 2029. I'll interject here the important point that now these calculations are done relative to the Earth. So I have a different gravitational parameter, the gravitational parameter for the Earth that's used here. In this table, the rows here are each hour, starting on April 12th at midnight UTC Universal Coordinated Time and running until midnight UTC on April 14th. Here I'm computing distance to the center of the Earth in kilometers and in miles, just as I had done before. And here at about 2200 UTC, that's about 6 p.m. on the East Coast, the distance is down to 23,853 miles. Oh, but the radius of the Earth, that's about 4,000 miles. So yeah, subtract off 4,000 mile radius of the Earth and the distance from Apophis to the surface of the Earth, just under 20,000 miles. Phew! Some of the other observations that I can make studying this data are the following. The specific energy here relative to Earth is positive, around 1.71 times 10 to the 7, meaning that Apophis is not in a bound orbit about the Earth. The positive specific energy indicates that. In fact, the eccentricity of the trajectory about Earth, it's about 4.25, and this indicates it's following a hyperbolic orbit relative to Earth. And while Apophis is affected by Earth's gravity, it's on an escape trajectory relative to Earth, and that's a good thing. I also noticed that jump in the velocity relative to Earth right around the moment of closest approach at 2200 UTC, when the speed jumps from about 6 kilometers per second to over 7 kilometers per second relative to Earth. That's about 17,000 miles per hour. Well, okay, now Apophis, the god of chaos, that's a hard act to follow, but let's take a quick look at two other examples. The Tesla Roadster launched by SpaceX in 2018, and the interstellar object Oumuamua. The Tesla Roadster, with a mannequin inside known as Starman, is orbiting about the Sun at a distance that takes it alternately out beyond the orbit of Mars and then back closer to Earth's orbit. This is position and velocity data downloaded from the Horizon system and the same calculations that I had run before. We see oscillations here in both specific energy and angular momentum, and the period of that oscillation appears to be close to the orbital period of Starman. That's about 18 months. But I really have no idea why, in the data I have here, that amplitude of the oscillation, that appears to decay slightly. All of the factors behind these fluctuations, they're really way beyond my area of expertise, but I still find it absolutely fascinating to explore. I do see a clear pattern in the data for the distance between Starman and the Sun, also with a period of about 18 months, which I know to be the orbital period of the Tesla Roadster and Starman. And it's just so much fun to consider that Tesla flying through space at around 60,000 miles an hour. And I see the peak in velocity about 75,000 miles an hour coinciding with the point in time when it is closest to the Sun, which is what I would expect, understanding basic orbital mechanics. And the calculations for specific energy and specific angular momentum that I'm doing here, they yield a value for the orbital eccentricity of about 0.25, and that's a value that we can confirm for the orbit of the Tesla on Wikipedia and through other sources. And finally, let's take a look at Oumuamua, an interstellar object passing through our solar system on an escape trajectory relative to the Sun. That is, Oumuamua is following a hyperbolic trajectory. Mathematically, that's a curve with an eccentricity greater than 1 relative to the Sun. Oumuamua is a Hawaiian word for scout, and when it was discovered in 2017, it was the first such interstellar object to be observed. It's also referred to as a hyperbolic asteroid, not a comet, since it doesn't have a coma or cloud of ice and dust that's expelled as it approaches the Sun. And yet it did appear to exhibit some non-gravitational acceleration, first suggesting to some early observers that it could be some kind of alien craft. Well, after many years now of studying it, there really is not sufficient evidence to support that hypothesis. The non-gravitational acceleration is most likely due to some outgassing that was not initially observed, or possibly due to the effects of solar radiation pressure. Still, this is a fascinating object. To pass through our solar system and escape the Sun's gravity, it has to be moving incredibly fast. Here, with another analysis with the Horizon data in the same way that I've done all these other calculations, I find the peak speed to be around 152,000 miles an hour relative to the Sun on August 30th of 2017. And I see that peak coincides with its closest approach to the Sun. With the Horizon data, I find the eccentricity of the orbit to be about 1.2, indicating that hyperbolic trajectory that I expect. And also fascinating here is that sudden spike in the specific energy right around the time of closest approach to the Sun, and also that jump discontinuity in the specific angular momentum. I really don't know what causes that, and I suspect it may be just due to measurement errors. I really don't know. Again, that would be a topic for further exploration another time. And speaking of further explorations at another time, where do we go from here? Is there a moral to this story? Vis-Viva is Latin for living force. It was the term used historically in physics for the animating force in the motions of objects. Perhaps sort of poetically, I feel like I've observed the signature of that animating force here in this data. And just already at the outset, I think it's deeply satisfying to see patterns hidden here within this huge table of numbers. Patterns that were not immediately apparent, but are there nonetheless. And I feel like I'm sort of on the right track when I see something that unifies those seemingly disparate values into any sort of pattern. How do they all connect? Well, here is some part of an answer to that. So, looking back on these two videos of the VisViva Lab, I've managed to demonstrate conservation of energy and angular momentum in the two-body problem, as illustrated in a dynamic model of a solar system Kerbal Space Program. That was in the VisViva Lab video part 1. And now here, we've explored the idea of conservation of energy and angular momentum using real-life data for celestial objects in our own solar system. And clearly, while these values are not truly constant, when considering only two bodies at a time, I've observed they are close to constant in the cases I've investigated, with some fluctuations, and also they exhibit some fascinating patterns. Ultimately, the values that are conserved are the entire energy and angular momentum of the entire system, scaling outward first to the solar system, the Milky Way galaxy, ultimately all masses everywhere in the entire universe. So, wrapping this up, guiding principles for understanding celestial mechanics in general are the equations of the conics, the mathematics of the two-body problem, and the resulting Vis-Viva equation. And broadening our view to the n-body problem, well, it invites in Apophis, the god of chaos. I'm only just grasping an understanding of the two-body problem. The n-body problem, that will always challenge, inspire, and impose some limits and demand some humility. Okay, so that's it. I'll end here. Thank you very much for watching, and I hope you found this video both interesting and educational, and that you enjoyed it as much as I enjoyed putting it together. Thank you again for watching.